Throughout our journey through chemistry so far, we've touched on the interactions between molecules. What about metal molecules, how they attract each other because of the sea of electrons in water molecules. But I think it's good to have a general discussion about all of the different types of molecular interactions and what it means for the boiling points or the melting points of a substance. So I'll start with the weakest. Let's say I had a bunch of helium. Helium, I'll just draw it as helium atoms. Look at the periodic table. And what I'm going to do now with helium, I could do with any of the noble gases. Because the point is noble gases are happy. Their outer orbital is filled. Let's say neon or helium. Let me do neon actually, because neon has a full 8 in its outer orbital. So we could write neon like neon, and it's completely happy. It's completely satisfied with itself. Neon. And so in a world where it's completely satisfied, there's no obvious reason just yet. I'm going to touch on a reason why it should be. If these electrons are evenly distributed around these atoms, then these are completely neutral atoms. They don't want to bond with each other, do anything else. So they should just float around, and there's no reason for them to be attracted to each other or not attracted to each other. But it turns out that neon does have a liquid state if you get cold enough. And so the fact that it has a liquid state means that there must be some force that's making the neon atoms attracted to each other. Some force out there, because it's at a very cold state, because for the most part there is not a lot of force that attracts them, so it'll be a gas at most temperatures. But if you get really cold, you can get a very weak force that starts to connect or makes the neon molecules want to get towards each other. And that force comes out of the reality that we talked about early on, that electrons are not in a fixed uniform orbit around things. They're probabilistic. And if we imagine, let me say neon now, instead of drawing it these nice and neat valence dot electrons like that, instead I could kind of draw its electrons as just it's a probability cloud, and what neon's atomic configuration is 1s2, and its outer orbital is 2s2, 2p6. Right? So it's highest energy electron. So it'll look, I don't know, it has the 2s shell, the 1s shells inside of that, then has the p orbitals. The p orbitals look like that in different dimensions. That's not the point. And then you have another neon atom, and it's these are, and I'm just drawing the probability distribution. I'm not trying to draw a rabbit, but I think you get the point. And watch the electron configuration videos if you want more on this. But the idea behind these probability distributions is that the electrons could be anywhere. There could be a moment in time where all of the electrons are out over here. There could be a moment in time where all the electrons are over here. Same thing for this neon atom. And if you think about it, out of all of the possible configurations, let's say we have these two neon atoms, there's actually a very low likelihood that they're going to be completely evenly distributed. There's actually much likelier, there's many more scenarios where the electron distribution is a little uneven in one neon atom or another. So if in this neon atom, temporarily, it's 8 valence electrons just happen to be like 1, 2, 3, 4, 5, 6, 7, 8. Then what does this neon atom look like? It temporarily has a slight charge in this direction, right? It'll feel like this side is more negative than this side, or this side is more positive than that side. Similarly, if at that very same moment I had another neon that had 1, 2, 3, 4, 5, 6, 7, 8, that had a similar, actually let me do that differently. Let's say that this neon atom is like this. 1, 2, 3, 4, 5, 6, 7, 8. So here, and I'll do it in a dark color because it's a very faint force. So this will be a little negative temporarily, just for that single moment in time. This will be kind of negative. That'll be positive. This side will be negative. This side will be positive. So you're going to have a little bit of an attraction for that very small moment of time between this neon and neon. And then it'll disappear because the electrons will reconfigure. But the important thing is to realize is that almost at no point is the neon's electrons going to be completely distributed. So as long as there's always going to be this haphazard distribution, there's always going to be a little bit of a I don't want to say polar behavior because that's almost too strong of a word, but there'll always be a little bit of a extra charge or one side or the other side of an atom, which will allow it to attract to the opposite side charges of other similarly imbalanced molecules. And this is a very, very, very weak force. It's called the London dispersion force. I think the guy who came up with this, Fritz London, who was neither, well, he was not London, he was not British. I think he was German American. London dispersion force. Dispersion force. And it's the weakest of the van der Waals forces. Van der Waals. I'm sure I'm not pronouncing it correctly. And the van der Waals forces are the class of all of the intermolecular, and in this case, neon, the molecule is an atom. It's just a one atom molecule, I guess you could say it. The van der Waals forces are the class of all of the intermolecular forces that are not covalent bonds and that aren't ionic bonds like we have in salt, and we'll touch on those in a second. And the weakest of them are the London dispersion forces. So neon, these noble gases, actually all of these noble gases, right here, the only thing that they experience are London dispersion forces, which are the weakest of all of the intermolecular forces. And because of that, it takes very little energy to get them into a gaseous state. So at a very, very low temperature, the noble gases will turn into the gaseous state. That's why they're called noble gases, first of all. And they're the most likely to behave like ideal gases because they have very, very small attraction to each other. Fair enough. Now what happens when we go to situations, when we go to molecules that have better attractions or that are a little bit more polar? So let's say I had hydrogen chloride, right? Hydrogen, it's a little bit ambivalent about whether or not it keeps its electron. Chloride wants to keep the electrons. Chloride's quite electronegative. It's less electronegative than these guys right here. These are kind of the super duper electron hogs, nitrogen, oxygen, and fluorine. But chlorine is pretty electronegative. So if I have hydrogen chloride, so I have the chlorine atom right here. It has 7 electrons. And then it shares an electron with the hydrogen. It shares an electron with the hydrogen. I'll just do it like that. Because this is a good bit more electronegative than hydrogen, the electrons spend a lot of time out here. So what you end up having is a partial negative charge on this side where the electron hog is, and a partial positive side. And this is actually very analogous to the hydrogen bonds. Hydrogen bonds are actually a class of this type of bond, which is called a dipole bond, or dipole-dipole interaction. So if I have one chlorine atom like that, and then if I have another chlorine atom, the other chlorine atom looks like this. If I have the other chlorine atom, let me copy and paste it right there, then you'll have this attraction between them. You'll have this attraction between these two chlorine atoms. Oh, sorry, between these two hydrogen chloride molecules. And the positive side, the positive pole of this dipole is the hydrogen side, because the electrons have kind of left it, will be attracted to the chlorine side of the other molecules. And because this van der Waals force, this dipole-dipole interaction, is stronger than a London dispersion force. And just to be clear, London dispersion forces occur in all molecular interactions. It's just that it's very weak when you compare it to pretty much anything else. It only becomes relevant when you talk about things with noble gases. Even here, there are also London dispersion forces when the electron distribution just happens to go one way or the other for a single instant of time. But this dipole and dipole interaction is much stronger. And because it's much stronger, or hydrogen chloride is going to take more energy to, one, get into the liquid state, or even more, get into the gaseous state than, say, just a sample of helium gas. Now, when you get even more electronegative, when this guy is even more electronegative, when you're dealing with nitrogen, oxygen, or fluorine, you get to a special case of dipole-dipole interactions, and that's the hydrogen bond. So it's really the same thing. If you have hydrogen fluoride, a bunch of hydrogen fluorides around the place. Hydrogen fluoride. Maybe I could write fluoride. I'll write hydrogen fluoride here. Fluoride is ultra electronegative. It's one of the 3 most electronegative atoms on the periodic table, and so it pretty much this partial charge is so it pretty much hogs all of the electrons. So this is a super strong case of the dipole-dipole interaction, where here all the electrons are going to be hogged around the fluorine side. So you're going to have a partial positive charge, partial negative side, partial positive, partial negative, partial positive, partial negative, and so on. So you're going to have this which is really a dipole interaction, but it's a very strong dipole interaction, so people call it a hydrogen bond because it's dealing with hydrogen and a very electronegative atom, where the electronegative atom is pretty much hogging all of hydrogen's one electron. So hydrogen sitting out here is just a proton, so it's going to be pretty positive, and it's really attracted to these negative side of these molecules. But hydrogen, so if we all of these are van der Waals. So van der Waals, the weakest is London dispersion. Then if you have a molecule with a more electronegative atom, then you start having a dipole where you have one side of where the molecule becomes polar, and you have the interaction between the positive and the negative side of the pole. It gets a dipole-dipole interaction. And then even stronger type of bond is a hydrogen bond, because the super electronegative atom is essentially stripping off the electron of the hydrogen, or almost stripping it off. I mean, it's still shared, but it's all on that side of the molecule. And since this is even a stronger bond between molecules, it will have even a higher boiling point. So London dispersion, then you have dipole or polar bonds, and then you have hydrogen bonds. Hydrogen. All of these are van der Waals, but because the strength of the intermolecular bond gets stronger, boiling point goes up. Boiling point goes up because it takes more and more energy to separate these from each other. In the next video, I realize I'm out of time. So this is a good survey, I think, of just the different types of intermolecular interactions that aren't necessarily covalent or ionic. In the next video, I'll talk about some of the covalent and ionic types of structures that can be formed and how that might affect the different boiling points.